Greetings and welcome, Internet friends. Mr. Waddy here, and today we're going to be learning an incredibly powerful skill for solving quadratic equations. Better than factoring, because factoring only works some of the time. Better than graphing, because graphing wasn't very convenient for finding answers when we had to approximate. And it's going to require one of our older skills, which was about factoring perfect square trinomials. And so I'm going to assume you all already know how to do that, but we'll do some quick warm-up on that. We'll also do an exploration in a second on discovering this, completing the square method. But if you feel comfortable with some of these things already and want to skip to perhaps the first example, go right on ahead. But here we are. So let's see. I suspect that I get warm-up question 2. I was going to say example 2. No, not quite. Notice I've only have a selected number of these warm-up questions. I suspect that this matches the perfect square trinomial in which a would have been y and b would have been 1 because the square root of 1 is 1. And the middle term is in fact equal to 2 times a times b, so that checks out. And I'm just going to mentally be doing that at this moment. And as a result, I can use the pattern. And because this is a plus sign, I'm going to use the plus version of the pattern. And it's just going to be a plus b all squared. So y plus 1 all squared. Boom, factored. All right, over here, a would equal x, b would equal 4, because the square root of 16 is 4. Is the middle equal to 2ab? 2 times x is 2x, times 4 is 8x. Yep. Notice it's got a minus sign there, so I'm going to do a minus b all squared. So x minus 4 all squared. Boom, got him. All right, let's see. Ooh, this one's a little trickier. A is going to be the square root of this, so that's 2a. B is the square root of 1, which is 1. 2ab, yep, 2 times 2a is 4a, times 1 is still 4a. And let's see, this is a plus sign, so I would do a plus b all squared. So 2a plus 1 all squared. All right, so we remember how to factor these perfect square trinomials. I suspect I notice them, by the way, anytime the first term and last term are perfect squares is how we identify them. And in this unit, we're going to be generating problems that are perfect square trinomials every time. And so the likelihood of them showing up is 100%. All right, here's a little, I know not everyone's a fan of algebra tiles, but here we go. Here's a little visual explanation about this idea of completing the square. And so so this expression here is the same, the blue tile is an x squared, the green ones are x's, so that's 4x. Then I've got an equal sign, and reds are negative, equals -2. So if I wanted to solve that equation, in the past, right, we would have maybe added 2 to both sides, tried to factor, it wouldn't work, and we couldn't solve it. All right, and so write the equation modeled, boom, we just did that. Notice one of the things that then they did, 4 algebra tiles are added to the left side to complete the square. What do you think complete the square means? Well, it turned this shape into a square. Yes. Why are 4 algebra tiles added to this side as well? Oh, well, that's the addition property of equality, right? If you add to one side, you got to add to the other. That makes sense. So the addition property of equality, I can add 4 here and 4 there, and equality is maintained. And so now notice the benefit of that is now that I have a square, I can write the dimensions of this square. So this whole thing is x squared, but its side length is plain old x and x. This is x in its value, but if this dimension is this x, then this dimension must be 1. And if this is 1 and this is 1, then this is 2. And so x plus 2 is this side length of the square, and also this side length of the square. That's also 2. So that's x plus 2. Let's simplify these. Well, the -2 and +4 is going to combine to be just plain old 2. All right? And so now the benefit here is, let's write the equation The area of a square, yes, could equal all of the little parts added together. Which actually, I didn't write that up here. Let's write this equation. So this was the same as, by the way, x squared plus 4x plus 4 was all of these little parts added together. And this was the equal to 2. Yeah, which they didn't ask for, they kind of did it later. But and so, yes, this is true, but even better than writing it this way, you'll see, is writing it as this times that, right? Multiplication taking place. And so I'm going to write this, and since I don't have enough space right here, I'm just going to write it on the side. I'm going to write this as x plus 2 all squared equals 2. And so here's the equation modeled by the algebra tiles, and let's solve the equation, in this case, using square roots. So instead of expanding this, notice what I can do. I can get rid of the square by rooting both sides, plus or minus, don't forget it, and I get x plus 2 equals plus or minus square root of 2, and then to get x by itself, I just subtract 2 from both sides, and this is in a radical, this isn't, so I can't, combine those in any way, and I get my exact answers. 2 of them are these. And if I wanted decimal approximations, which we'll visit probably in another example in a minute, I could actually literally do -2 plus the square root of 2 and -2 minus the square root of 2. And so this is solved. This problem would never have been factorable, but I'm able to get an exact answer using this little trick called completing the square. Is visually what's happening. All right, and so here, what would I have to do to complete the square? Well, okay, let me write the equation first. So this would have been x squared plus 6x was equal to -5. To complete the square, I would have had to add, what? 9 little 1x1s, 1x's, algebra tiles. And so that's the same as adding 9 to both sides. And so I would get x, now I can write the dimensions of this square. That's x plus 3 times x plus 3, which, by the way, is the factored version of this expression. And we'll do some non-algebra tile ones in a minute, don't you fret. And let's see, if I have -5 plus 9, that's the same as 4. And now I can solve. Oh, this problem would have been factorable if I solved it. So I get, when you root both sides, plus or minus, don't forget it. X plus 3 equals plus or minus 2. And then subtract 3 from both sides. And I get, behold, x equals -3 plus 2 is -1. -3 minus 2 is -5. And so there's my 2 answers. And to be honest, I think this route, in many cases, is the easier route. But, I mean, we spend a lot of time on factoring, and so sometimes people are more familiar with one route. Thereby, the familiarity is making it, quote-unquote, easier for them. So here's the completing the square strategy. If I have some expression where there's an x squared and a linear term, an x term, I can add a constant to both sides of the equation, or to this expression, and create a perfect square trinomial. I'm completing the square. And now to figure out what do I add to both sides, well, well, where did this 9 come from? Well, it turns out there is a relationship that the new c term is equal to b divided by 2, right? 6 divided by 2, I got 3 here, so I got half of it. And then I, to find the length, dimensions of this square, right? It's 3 times 3, but the area would be that value squared. And so 6 divided by 2 was 3, 3 squared was 9. Let me check up here. Here's the b term. 4 divided by 2 is 2, and 2 squared is 4. Okay, so that's kind of what their little shortcut is. So find 1/2 of b. of the, right, the x term, square the result, and then add that. So I like to say, and you could write this down, the new c term is going to equal b divided by 2 all squared. And actually, one of the things I was thinking about, I've got some like Waddy Math videos from 7 years ago showing how to do this. So you could go, maybe we'll do a little walk down memory lane, check out some old school Waddy Math videos. So here we go. All right, example 1. We've made it. Complete the square for each expression, then factor the trinomial. All right, so my new c term is going to be b divided by 2 all squared. So here b is equal to the 6. I'll work in orange here, I guess. So I usually do this work aside, kind of like when we were factoring, and I'd have the factors listed, like 1 and 4 and 2 and 2. So work aside. So to find my new c term, I'm going to do 6 divided by 2 all squared. That's 3 squared, which is 9. And so to complete the square, I would add 9 here. Now, this is not an equation. I'm, figuring this out. They're just asking me to complete the square and then factor what's left. And in order to factor, because it's a perfect square trinomial, it's going to equal the a plus b all squared. So a would have been the x, and b would have been the square root of 9, which is 3. Right? A would have been x, and oh dear, you know what's rough here? I'm not going to use the a equals b equals thing because I've already got b equals to the b terms coefficient, and I don't want to cross-pollinate multiple meanings of the same variable name if I could avoid it. But also, this 3 comes from multiple locations. It is half of the b term, which is the easiest way. It is the square root of my new c term. Multiple ways you could find it. It's the thing that I had before I squared it, right? Multiple ways of validating your outcome. Now, it gets a little bit trickier whenever b is odd, because dividing an odd number by 2 is going to result in fractions. But here's a little bit of an explanation. So here's the expression. If I have x squared plus bx, right, represented here, notice this is one of the ways they are saying you could make a square. Well, take whatever b is and chop, 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 and move it down over here. And now these are the 2 halves of whatever b was. And then the complete the square part would be that number b over 2 squared. And that would give you the remaining piece. And so that's kind of like a nice visual explanation as how this works. And now the unfortunate thing is if b is odd, you're going to get fractions. But fractions are real. That's perfectly fine. So here's my new c term. -9 divided by 2 all squared, right? Because b was the -9. And now let's just square this using properties of exponents. Negative all squared is going to become positive. 9 squared is 81, and 2 squared is 4, and so I would add 81/4 to both, or blah. If it was an equation, I would add it to both sides. And then to fast factor this, it's just going to be a minus b all squared. So x minus, what number is it going to be? Well, it's going to be half of 9. Which is 9 halves, or 4.5 if you want to think about it that way. And so, yeah, there we go. Let's keep cruising. So here, let's find my new c terms. So that would have been 10 over 2 all squared. So 5 squared is 25. And so I would have added 25. And then fast factor would have been an x plus something all squared. And what is that something? It's half of this. It's the square root of that. It's the same thing that I had here. Tell you what, I'll do the fractiony one. So my new c term would have been 7 halves all squared. Square both of those, top and bottom, because this fraction did not simplify. That's 49/4 And so I would have added 49/4 there, and then fast factor, it was a plus, so I'd have x with a something all squared, x plus 7/2, right? And that's half of your b term, that's the square root of this thing, or it's the thing that I had before I squared it. Boom, multiple lines of confirmation. Okay, so how do I use this to solve equations? Well, you're gonna just add that new c term to both sides. So here we go. Here's an equation. Oh, I didn't give myself a lot of room here, did I? So let's find our new c term. So that's going to be -16 divided by 2 all squared. That's equal to -8 all squared. Parentheses are important here, which is equal to 64. So I'm going to add 64 to both sides of this equation. And I'm going to fast factor this right now. All right, so I'm going to have a minus b all squared. A is the x, b is half of 16, which is 8. 64 minus 15, well, 64 minus 10 is 54. Looks like 49. And now, in order to solve, I'm going to, because this has been fast factored and the whole thing's squared, I can just root both sides, plus or minus, don't forget it. I get x minus 8, because the square root and the square cancel out. That's a sad looking plus or minus. Plus or minus, the square root of 49 does simplify in this case. I get 7. And then add 8 to both sides. I get x equals 8 plus 7 is 15. 8 minus 7 is 1. There are both of my answers. The fact that these answers, by the way, don't have any square roots or radicals attached to them suggests that the original problem technically would have been factorable. I was tempted. All right, tell you what, I'm going to do it. I'm going to do it. You don't write this down. If I was factoring, I would have added 15 to both sides to get this equal to 0. I would have found the factors of 15, 1 and 15. This one's not that bad for factoring. Which of those add to be 16 would have been these. I would have had an x with a 1, an x with a 15, right? And when it factors, then yeah, it works, and you're fine. And then I would have 0 product property, set each of those factors equal to 0. And then I would have solved, I'd get x equals 1, x equals 15. So there's just confirmation that the factoring way still works, but only on problems that are factorable. And not all of them will be. Although these ones, they happen to be. Tell you what, let me do this one. So, new c term. I would take the b divided by 2 and square it. So that's 6 squared, which is 36. And so I would add 36 to both sides. As fair is fair. This expression is now a perfect square trinomial. I would have had m plus 12 divided by 2 was 6, right? This number that I had before I squared it is always going to be my fast factor. 36 minus 8 is 28. And now we can root both sides, plus or minus. Ooh, I've got to use some properties of radicals here. So I get plus or minus square root of 28. Is there a perfect square that goes into that? Yes. Square root of 4 and 7. And so we will subtract 6 from both sides to get m by itself. And I get -6 plus or minus square root of 4 was 2. Square roots of 7. And so this is the exact answer. But notice they wanted us to round our solutions to the nearest hundredth, 2 decimal places. And answers, plural, is what I've got. So in my calculator, I'm going to type -6 plus second square root, or 2 second square roots of 7. And one of my answers is -0.71 when I round it. And the other one, if I just hit the up arrow and over, change the plus to a minus sign, I get -11.29. And so there's my two answers, rounded to 2 decimals. Not bad. And the fact that this had a radical in the answer for the exact means this problem could never have been solved by factoring. So hooray, hooray. Let's see. Oh, wow, I think the video's done. I'm going to do this foreshadowing. I'm going to do this problem in the next video. What do you do when there's a number in front of the squared term? That's weird. All right, well, thanks for watching, Internet friends. Have a great day.